Okay, this is another sample final exam. That's how it's listed at the D2L site. And there's a written solution to this exam at the D2L site. But I thought some of you might want to watch me go through the problem step by step. I just want to point out a couple of things. These equations on the first 2 pages of the sample exams, those are going to be the same equations that you'll have at the front page of your online exam. The problem, though, is that once you turn the page and start answering questions, you can't go back to that first page to see these equations. So I would encourage you to print out these pages and have them sitting next to you, next to your computer when you take that exam. I would also encourage you to have a lot of scratch paper, because these aren't problems that it's not a history test where you can just say, oh yeah, that happened in 1936. You're going to have to draw extended free body diagrams and work out the equation, and so you should have some scratch paper there. Okay, let's get started. As an aside, this is the second time I've gone through this. The first time I recorded for over an hour, and just as I was finishing the last page, the software crashed. So we're going to do this again. Okay. We've got Shannon going up this hill in a really interesting skateboard that has 2 wheels, a large one that has a radius of 0.4 meters and a small one that has a radius of 0.25 meters. And we're told that she's initially traveling up the hill with an initial velocity of 20 meters per second. And you know what's going to happen. She's going to go up, she's slowing down as she goes, and then 4 seconds later she's going to stop at the top and turn around and go back. But we're just going to look at that time she's going up the hill. Now, we know that in order to go up, her wheels have to rotate, as far as our perspective, counterclockwise from the side we're looking at. And by right-hand rule for omega, if I curl the fingers of my right hand in the direction that wheel is turning, that's going to give me the direction of omega, which is out of the page. Okay. Now I know that as she goes up that hill, she's slowing down. And so that means that her alpha vector has to point opposite the omega. Now, the omega is out of the page by right-hand rule. Okay, but there's no right-hand rule for alpha. Alpha, you got to use some reasoning. If it's speeding up, going faster and faster, then that's going to be in the same direction as omega. If it's slowing down, that's going to be in the opposite direction. So I would say that this is into the page because it's slowing down. Okay. Now, we're asked in this first part, what is the initial angular velocity, the omega, magnitude and direction, of each wheel? Now, we've already found the direction. We just discussed that. Let's talk about the magnitude. And we know that the initial linear velocity is 20 meters per second. And we have this rolling condition that we presented last Wednesday in class, in lecture. And the rolling condition is that the velocity in the linear direction is proportional to the angular velocity of the wheel. And the proportionality constant is the radius of the wheel. Okay? That's the rolling condition. It should be called the rolling without slipping condition. But that's going to be able to give us the angular velocity if we know the linear velocity and the radius of the wheel. So let's look at the back wheel. The back wheel, I'm going to have an omega that's equal to 20 meters per second divided by a radius of 0.4 meters, and that's going to give me 50 radians per second. And as we said, that's out of the page. The front wheel, we just do the same thing. Okay, we take the 20 meters per second, but this time we divide it by the smaller radius of 0.25 meters, and we get 80 radians per second. Okay. Now, how far up the hill does she travel? Well, this is a linear kinematics problem, and you know that to solve those, you first of all make your list of the 5 linear variables: displacement, acceleration, initial velocity, final velocity, and time. And in order to solve these problems, you need to know 3 of those variables. Well, we know that she starts with a velocity of 20 meters per second. And I put that in as a positive 20 meters per second because I'm choosing a coordinate system where up the ramp is going to be called positive x and down the ramp is going to be called negative x. I have the freedom to choose my own coordinate system. I just need to stay consistent throughout the problem, keep using that same coordinate system. Now we know that when she gets to the turnaround point, the final point, she stops. And she does that, we're told, 4 seconds after she starts. So I've got 1, 2, 3 pieces of information, and I want to know how far she travels. That's my delta x. And that makes the acceleration the who cares. Well, that tells me which of the kinematic equations that I should use. I need to use the equation that doesn't have a in it. Well, that's this second one here. Okay, there's no acceleration in that second equation. So I say delta x is equal to 1/2 v initial plus v final delta t. And that means I have 1/2 of 20 meters per second plus 0 times 4 seconds. And that's going to give me 40 meters. Okay, so she's going to travel 40 meters up that hill before she stops and turns around. Now, through what angle, delta theta, does each tire rotate during the motion up the hill? Well, this rolling condition has a counterpart. The linear displacement is proportional to the angular displacement, and the proportionality constant again is the radius of the wheel. We talked about that last Wednesday. So if I use that rolling condition on the back wheel, well, I would have my delta theta is equal to 40 meters. That's how far you traveled up the hill, divided by 0.4 meters. And that's going to give me 100. And the units here would be radians, because we're talking about an angle there. Okay. For the front wheel, we do the same thing, but this time we divide by the smaller radius of 0.25 meters, and that gives me 160 radians. Okay. Now, we're asked about the magnitude and direction of the angular acceleration, that's alpha, of the back wheel at the turnaround point. Okay, magnitude and direction. We have a third rolling condition. You can see the pattern here, and that is that the magnitude of the linear acceleration is proportional to the magnitude of the angular acceleration. And again, the radius of the wheel is that proportionality constant. Okay? Now, so the first thing we need to do is figure out what that linear acceleration is. Well, that's the part that we didn't care about up here, and now we do. And so let's use the equation that doesn't have delta x in it. That would be v final is equal to v initial plus a delta t. So I'm going to have 0 as my final velocity. I start with 20 meters per second, and I am having that acceleration for 4 seconds. Okay, now we know that that's constant acceleration because she's going up a constant slope. And that's important because that's the only way we can use these equations. Well, that's going to give me an acceleration of negative 5 meters per second squared. Well, what does that mean? Well, what that means is that the acceleration is 5 meters per second every second down the ramp. Okay, that minus sign, we set up our coordinate system such that the minus sign means down the ramp. Okay, now if I use my rolling condition here, that gives me that the magnitude of the angular acceleration is going to be 5 meters per second squared divided by the radius of the big wheel, 0.4 meters, and that's going to give me 12.5 radians per second squared. Okay. Now, what about the direction? Just like the linear velocity stays the same magnitude and the same direction all the way up and down the ramp, so is also true for the angular acceleration. Okay, we already said that when she's going up the ramp, the angular acceleration was into the page because she's slowing down with an omega out of the page. When she's coming down the hill, her omega would now be into the page and she's speeding up, so alpha would still be into the page. But what about the turnaround point? We know that the omega at the turnaround is 0. Okay, but that doesn't mean that the alpha is 0 there. Certainly not. If the alpha were 0 there, the omega wouldn't change. And so what we have to do is we have to recognize that alpha is going to be the change in omega that happens over some time interval. Okay, so I need 2 measurements. I need a final omega and I need an initial omega. And I'm going to take the initial omega to be just right before the turnaround point. So that initial omega, she's still going up the ramp, so her omega is still out of the page. The final omega I'm going to be taking as right after the turnaround point, when she's going back down And now the wheel's turning the other way, the omega would be into the page. Well, what do I have to add to a vector out of the page to turn it into a vector into the page? Well, I've got to add a change vector that's into the page. And that means that alpha is into the page, because alpha is always in the same direction as the change in omega. That's because time always marches forward. It's always a positive number. So these two vectors are always in the same direction. So the answer down here is going to be that the direction would be into the page. Okay, to avoid the problem that I had last day, I'm going to end this recording. Okay, let's look at this Yogi Bear problem. We've got Yogi who has trapped Ranger Smith out on the end of a log. He's kind of in a bad predicament there. And we notice that the log is touching the ground at two places, A and B. And we're given the mass of Ranger Smith and the mass of Yogi, yikes. And we're told that the log is 6 meters long and that 4 meters of the log is hanging out beyond the cliff there. So we're first asked to draw an extended free body diagram for the log. So let's do that. Now, folks, I'll point out that in a multiple choice test, there's not going to be any place on that test where you can draw an extended free body diagram and get points. But a lot of those problems on the final are going to require you to draw a free body diagram on your scratch paper if you want any chance of getting the right answer. And the first force you're going to put on that diagram is always going to be the weight force Earth on the log. And then you ask, are there any magnets in this problem? No. So what touches the log? Well, we've got Ranger Smith pushing down on the log, and he pushes with a force. Oops, that's not a weight force, is it? No, that's a contact force. That's a normal force by Ranger Smith on the log. And I know that that's going to be 1,000 newtons. How do I know that? Because if I draw a free body diagram for Ranger Smith, I know that he has a weight force that's going to be his mass, 100 kilograms, times g, which is 10, or 1,000 newtons. And if he has no acceleration, if he's just standing there looking perturbed, then that means the only other force on him, which is the normal force by the log on Ranger Smith, must also be 1,000 newtons. By Newton's second law with zero acceleration. And I know by Newton's third law that this push up on Ranger Smith by the log is equal to the push by Ranger Smith down on the log. And so that's how I know that this is 1,000 newtons. In the same way, I know that Yogi is pushing down with a normal force, Yogi on the log, that's 3,000 newtons. And then I have the ground, and the ground is pushing up at A with a normal force on the log, and then also here at B with a normal force, B on the log. And that's my extended free body diagram. Those are all the forces. And you see a mistake there. This should be 3,000 newtons, not 300 newtons. Yogi's diet is all picnic baskets, so he's been eating a lot of them. Now, we're asked to find the torque, magnitude, and direction exerted on the log by Ranger Smith about a pivot at point B. We're going to make that our pivot point right there. And if I look at that torque. The magnitude of that torque by Ranger Smith is going to be the push, which is the normal force by Ranger Smith on the log, times the lever arm of Ranger Smith. Okay, well, that to be 1,000 newtons. That's what we have here. And then the distance from the pivot to where that force is applied. Okay. So that's going to give me 4,000 meter newtons. Now I could also call that a Newton meter, but we've reserved Newton meter for, we call that a joule, and we reserve that for energy. And this is not an energy, this is a torque. Now the direction is given by another right-hand rule for torque. And that right-hand rule, we sometimes have to turn our paper so that we can start at the pivot and reach with our right hand out to where the force is applied. So we physically reach our right hand out to where that force is applied. And this is the important part, folks. This is where it all happens. You have to turn your wrist so that you can wave your fingers in the direction of the force without breaking your wrist. That forces your thumb into the direction of the torque. So again, I start at the pivot, I reach out to where the force is applied, turn my wrist so that I can wave in the direction of the force. My thumb is now pointing into the page. Okay, so that means that the direction is going to be, direction is going to be into the page. Okay, now part C is where all the interesting stuff happens that deals with balancing torques. We're told that the mass of the log is 150 kilograms. That means that this weight force on our free body diagram is going to be 1,500 newtons. Well, we're asked to find the normal force exerted by the ground on the log at point A. So we're looking for this force here, A on the log. Okay? Now, I have two unknown forces left in my free body diagram. I don't know how hard the ground's pushing at A, and I don't know how hard the ground's pushing at B. And, you know, I'm only interested right now in one of those two. I know that if I know one of them, I can find the other one really easy, because the old rules still apply. All the force up has to balance all the force down, and I know that I've got 5,500 newtons down when I add this all up. So whatever I got here, this plus this has to add up to 5,500 newtons. But if I want to find this one all by its onesies, I got to eliminate this one from my equations. And I do that by balancing the torque about this pivot at point B. Because if I put my pivot there, I get no torque from this normal force by B. Okay? So if I balance all the clockwise torque with all the counterclockwise torque about point B, then I only have the one unknown force in my equation. Well, what I need to do is decide which of these forces are trying to make that log rotate clockwise about this pivot. Again, I play a little mind game where I pretend there's a great big golden spike going right through the log, forcing to rotate at that point. And then I ask for each of the forces, is this force trying to make it go clockwise or counterclockwise about that pivot? Well, this normal by A is trying to make it go clockwise about the pivot. Likewise, the weight force is trying to make it go clockwise, the push by the Ranger clockwise. The only force that's trying to make this whole log rotate about the pivot counterclockwise would be the push by Yogi. And so I would put my equation, the normal by A on the log times its lever arm, or distance to the pivot. Well, that's going to be 2 meters. And then I would take this weight force of 1,500 newtons times its lever arm, and this is just 1 meter. And then I would have the force of 1,000 newtons by Ranger Smith, and it's got a lever arm, we said, of 4 meters. And that has to balance the 3,000 newtons by Yogi acting at its pivot point, its lever arm. It's 2 meters from the pivot. Okay. Now, when I work this out, I get the normal by A on the log times 2 meters is equal to 500 meter newtons. And if I just divide both sides by 2 meters, I get this normal force by A on the log is equal to 250 newtons. Okay? Now, as I said before, if I know one of these unknown forces, I can quickly find the other just by balancing all the upward force. That would be the normal by, well, let's just write it out. Okay, let's say 250 newtons plus the normal force by B on the log. That's all the force up. That has to balance all the force down, which would be 3,000 from B, 1,500 from the log, and 1,000 from Ranger Smith. And that's going to give me a normal force by B on the log of 5,250 newtons. Yikes. So I really didn't draw this arrow long enough. That should be a little bit longer. Okay. Okay, now this last part proved to be the most difficult part of the whole exam. This is where people really had a hard time. We're told that Ranger Smith finally gets fed up with being humiliated, and he decides to turn the tables on Yogi. So he jumps straight up into the air, and in doing so, causes the log to tip, to rotate, and the question is, what minimum acceleration up would Ranger Smith need to make this happen? And so, first of all, let's talk about why jumping up in the air would make that happen in the first place. Well, if we draw a free body diagram for Ranger Smith, his weight force is going to stay 1,000 newtons without diet or exercise. You know, nothing he does can change that other than diet and exercise. But if he jumps up such that he has an acceleration in the upward direction, that means that the normal force, the only other force on him that's exerted by the log on Ranger Smith, is going to be bigger than 1,000 newtons. Well, by third law, if the force up on Ranger Smith by the log gets bigger, then the force down on the log by Ranger Smith gets bigger. And if this force gets big enough, we can cause the whole thing to rotate. Now, what does it mean to actually tip? Well, this thing is going to tip when that contact point at A whoops, better show the picture. When that contact point at A is no longer a contact point, okay? When the log stops touching the ground at A, then we're tipping, okay? So what does that mean? If the log's not touching A, what does that say for this normal force by A on the log? Well, it's got to be 0. So our condition for tipping the log is we need to find the normal force by Ranger-Smith on the log such that the normal by the A on the log goes to 0. Okay? So what we're going to do is we're going to balance all the clockwise torque with all the counterclockwise torque again. But this time we're going to do it with no contact force at A from the ground. And we're going to solve for what push is required to make that happen from Ranger-Smith. Okay, so let's do that same equation that we had here, but now this is going to be 0, and the unknown is going to be this push by Ranger-Smith. So what we're going to have is we're going to have the 1,500 newtons with 1 meter lever arm. We're going to have push by Ranger-Smith on the log, and his lever arm is meters. And that's got to balance the 3,000 newtons times its lever arm of 2 meters. Well, that's going to give me a normal by Ranger-Smith on the log of 1,125 newtons. Okay? Now, if I plug that in and if I use Newton's third law and say if Ranger-Smith is pushing that hard on the log, then the log's pushing that hard on Ranger-Smith. Now I can see that this free body diagram for Ranger-Smith screams up. And I can find the acceleration by using Newton's second law. F net equals ma. Now I've kind of boxed myself in here. Let me do that. I've got 1,125 newtons up, so that's positive. And I've got 1,000 newtons down, so that's negative. That's going to equal the mass of Ranger-Smith, which is 100 kilograms, times A. And that's going to give me an acceleration of 1.25 meters per second squared up. Okay, so any acceleration of Ranger-Smith greater than that is going to tip that log, which is a problem for Ranger-Smith ultimately. Okay, again, I don't want to lose my work, so I'm going to end this recording now. Okay, let's look at this buoyancy problem. We have 3 different beakers, graduated cylinders, if you will, each with a different liquid in it. We're given the density of liquid B and liquid C, but not of liquid A. We're told that all of these beakers start out filled to the same level, 25 milliliters. And remember, 25 milliliters, a milliliter is the same as a centimeter cubed, which sometimes we write as centimeter cubed. Those are all different ways of saying the same thing. If you're in the medical profession, if you're a doctor or a nurse, you most likely talk about these volumes in terms of milliliters, whereas in a science class you more often use centimeters cubed. But they mean the same thing. Now, we're told that we have a ball, and that when we put that ball in liquid A, it sinks to the bottom. And we know that when it sinks to the bottom, the level in this beaker goes from 25 up to 40. Okay. And and we also know that if we put that same ball in liquid B, it floats such that 2/3 is beneath the surface and 1/3 is above the surface. Okay, so what does that tell us? Well, first of all, we can easily find the volume of the ball, because in a situation where it sinks, where the ball is now, liquid A used to be, and that liquid A had to go somewhere else. And that somewhere else is, well, up here. Okay, so the difference in the reading here is going to be the volume of the ball, rather. So I can write the volume of the ball is going to be the final reading of 40 milliliters minus the initial reading of 25 milliliters, and that's going to be 15 milliliters, which is 15 centimeters cubed. Okay? So when something is submerged, like the ball, it displaces its entire volume when submerged. Okay, so this difference here is 15 milliliters. Okay, now we want to find the mass of the ball. Well, when you're looking for the mass of something, you want to look for an experiment where it floats, because we know that when something floats, there's only two forces acting on it. We have the weight down, which is the mass of the ball times g, and we have the buoyant force up, and that's equal to the mass of liquid B that's displaced times g. And if it's floating, it's just sitting there, it has no acceleration. Okay? So if we knew how many grams of liquid B were displaced, that would equal the mass of the ball. And so we know that the volume of the ball is 15 centimeters cubed, and 2/3 of that is displacing liquid B. Okay, so that means the mass of the ball is equal to the mass of liquid B displaced. Well, that's going to be 2/3 of 15 centimeters cubed times the density of 1.2 grams for each centimeter cubed. Well, the centimeter cubes are going to cancel. 2/3 of 15 is 10. 10 times 1.2 is 12, so that's going to be 12 grams. Okay. Now, if we want the density of the ball, and that's only worth 2 points, I just get the density of the ball by taking the mass of the ball and dividing by the volume of the ball. Well, that's going to be 12 grams divided by 15 centimeters cubed, and that's going to be 0.8 grams per centimeter cubed. Okay. Now, there's another way to solve this. Just like you can dance forwards or backwards, unless you're a guy, we can solve this problem either forwards or backwards. Let me turn the light back on. The other way to solve it is to recognize that this ball is floating with 2/3 of its volume submerged. We said in class that if an iceberg is floating with 90% of it submerged, we showed that meant that the density of the ice was 90% of the density of the water. Okay, and so we can work this backwards by solving part C first. Let me put a C prime here, and I can say that the density of the ball is equal to 2/3 of the density of liquid B. Well, that's going to be 2/3 times 1.2 grams per centimeter cubed. Move that up. And lo and behold, that gives me the same answer I got before, namely 0.8 grams per centimeter cubed. Well, now if I know the density of the ball, I can go back up here to B and say, we'll call that B prime now. I can say, well, the density of the ball is equal to the mass of the ball divided by the volume of the ball. Well, that means 0.8 grams per centimeter cubed is equal to the mass of the ball divided by 15 centimeters cubed. If I solve that for the mass of the ball, I get 12 grams, just like I got, just like I got over here. So whether I find the mass first and then find the density, or whether I use the iceberg principle to find the density first and then go back and find the mass, it's all the same. It's all the same. Okay. Will this ball float or sink in liquid C? Well, you see that clearly it's going to have to float. And I say that because the density of the ball, which we found to be 0.8 grams per centimeter cubed, is less than the density of liquid C, which is given to be 0.85 grams per centimeter cubed. And so it has to float. Now, I could even ask you, what percentage of the ball is submerged, and you would just essentially take the ratio 0.8 over 0.85, and that would be the percentage of the ball that is submerged. But I didn't ask that in this question. The last question, is the buoyant force on the ball greater in liquid A or liquid B? Well, this one turned out to be a little tricky. Some students wanted to say, hey, in liquid A, it's displacing all of its volume, all 15 centimeters cubed, whereas in liquid B, it's only displacing 2/3 or 10 centimeters cubed of liquid. But if you make that argument, you're comparing apples to oranges, because it's not the volume of liquid displaced that determines the buoyant force. It's the mass. It's the weight of the fluid, which is proportional to the mass, that determines that buoyant force. And even though I'm displacing more cc's of liquid A than liquid B, they don't have the same density. And indeed, I don't even know the density of liquid A, so I couldn't even calculate how many grams of liquid A are being displaced. What I do know is that it's the same ball in both cases with the same weight. And if I look at the ball in liquid B, I know that that weight, whatever it is, well, I know what it is. It's 0.012 newtons. I just made that into kilograms and multiplied by 10, but that's not important. The ball has the same weight whether it's in liquid A or liquid B. And in liquid B, the buoyant force is big enough to float it, to give it zero acceleration. Whereas that same weight of the ball in liquid A is not supported. The buoyant force is smaller than the weight. I know that because it accelerates down to the bottom of the beaker. So I would answer this question by saying the buoyant force is, got to look at the page, greater in liquid B. Okay, and my reasoning is that the buoyant force is equal to the weight of the ball in liquid B, because it floats with acceleration equal to zero, and the buoyant force, yeah, you can see that. The buoyant force is less than the weight in liquid A because it sinks with acceleration down. Okay, and that's been that third problem. I'm going to stop the recording temporarily. Okay, let's look at the multiple choice questions on this practice exam. In the first problem, we have two objects that have different masses but the same kinetic energies. If you use the same retarding force or friction force to stop them, which one will stop in the shorter distance? Well, we're dealing with energies here, so we want to use the energy equation. The general energy equation, of course, is that energy initial is equal to energy final, except when it's not, and it's not when there's an external Verk. Now, in this case, we're on a level surface, I assume, and so there's no gravitational energy we have to worry about, and there's no springs. So what we're talking about here for energy is kinetic energy. And if it's a retarding force, like a friction force, it's pushing opposite the motion. So that's going to be a negative Verk, the force by the distance. And if we bring it to a halt, it won't have any kinetic energy at the end. We're told that even though they have different masses, I've got the same initial kinetic energy and the same retarding force. Well, if you look at this equation, if it's got to be the same for both, the only way to solve that is if delta x is also the same. So the answer is C. Now, the second problem is very similar in syntax. It sounds the same, but it's a very different concept. Now, two objects that have different masses, the same momenta, okay, mass times velocity. If you stop them with the same retarding force, which one will stop in the shorter distance? Well, the fact that we're dealing with momenta means that we've got to start with this momentum equation, which is that the initial momentum plus an impulse gives me the final momentum. Now, if I choose, let's say, to the right to be the positive x direction, then I have my initial momentum. If this retarding force is going to slow things down, it's got to be pointing in the opposite direction of the momentum. So if the momentum's positive, the friction force would be negative. And now the impulse is force times time, not distance. And if we stop it, it has zero momentum. So let's make the same sort of arguments. If we start with the same momentum and we use the same retarding force, that means that delta t is the same. Well, that's not what they asked. They didn't ask which one stops in the shorter time. They asked which one stops in the shorter distance. Well, if they've got different masses, then the lighter one is going faster than the heavier one. Okay? We can either have a small mass with a big velocity or a big mass with a small velocity. And clearly, if the time to stop them is going to be the same, the one that's going to go the shorter distance will be the one that's moving the slowest. And so that will be that it'll be the shorter distance would be for the heavier object. That would be B. Now, this problem was in the third midterm. You recognize it, but we'll work it really quick. We have this bob. It starts from rest 2 meters above the floor, and we want to know when it gets here, how fast is it going? And that's just an energy problem. The energy initial is equal to the energy final, except when it's not, if there's Werk done by an external agent. Now we know that a string is always pulling along the string, and the ball is always moving perpendicular to the string, so that gives me 0 Werk. The initial energy is all gravitational. The final energy is all kinetic. And so that's going to give me a V final equal to the square root of 2GH. And we found that to be 6.3 meters per second. And so the answer is A. Now, a ball rolls down a 10-meter slope. The ball starts from rest at the top and reaches the bottom 8 seconds later. What is the ball's final velocity? Well, people were tempted to just take the 10 meters and divide by the 8 seconds, and that gives them 1.25 meters per second. But that would be the average velocity, not the final velocity. This is a kinematics problem. We start all kinematics problems by making our list of variables. And we have to know 3 of these to proceed. We know that it travels 10 meters in 8 seconds, and it starts from rest. There's 1, 2, 3 things that I know. And I'm looking for the final velocity at the bottom of that incline. That makes the acceleration the who cares. And so I use the equation that doesn't have acceleration in it, namely that delta x is equal to 1/2 v initial plus v final delta t. And we start from rest here. So that means that 10 meters is equal to 1/2 times v final times 8 seconds. And that's going to give me a v final of 2.5 meters per second. So the answer is C. So in 5, we have a student standing on the edge of a tall cliff. She throws her textbook up into the air at 15 meters per second. It goes up and comes back down. And we want to know where is that that textbook relative to her 5 seconds later. Well, again, this is a kinematics problem, one-dimensional kinematics. Since it's up and down, I'm going to use delta y instead of delta x. The difference between this and the last kinematics problem is that this is a free fall problem, and if I choose up to be my positive y direction and down to be my negative y direction, then I can automatically put in my acceleration is negative 10 meters per second squared. My initial velocity, If down is negative, then up is positive, so this is going to be a plus 15 meters per second. And the time we're given is 5 seconds. We're looking for how far this book is away from its initial location, where it was thrown, and that makes the V final the who cares. So I use the equation that doesn't have V final in it. Okay, and so that's going to give me 15 meters per second times 5 seconds plus 1/2 times negative 10 times 5 seconds squared. Well, that's going to be 75 meters minus 125 meters equals negative 50 meters. Well, the negative sign just means that the book ends up below its initial location by 50 meters, but we're just asked how far away is the book, and so the book would be 50 meters away from the student. So the answer is C. Now, if I go to the top of that next page, we have a standard collision problem. Because it's a collision problem, we conserve momentum. Since that's a vector equation, we need a coordinate system. Let's call to the right positive, to the left negative. We're told that we start with a 4 kilogram block that's going to the right at 12 meters per second. Well, that's 4 kilograms times 12 meters per second, and it's to the right, so it's positive. And it collides with a 6 kilogram block that's moving left, also at 12 meters per second. So I got 6 kilograms moving at 12 meters per second. And that's negative momentum. Then we have the collision. That's what the equal sign means. And right after the collision, the small block, the 4 kilogram block, is moving at 3 meters per second, but it's moving to the left, so that's negative momentum. And then I have the 6 kilogram block, but I don't know how it's moving. That's what the question's asking. So I make its velocity a positive variable, Vf, and I solve for Vf. If I get a positive number, it's going to the right. If I get a negative number, it's going to the left. When I solve this, I get Vf is equal to minus 2 meters per second, which means it's going 2 meters per second to the left. So I come back here and put C for number 6. Now, we have Professor Steve Eiger, a noble knight of the Round Table, pulling with 800 newtons, and he's pulling in a direction that's an angle 37 degrees with respect to the direction of the position vector. So this would be my force, this would be my position vector, and the angle between them is 37 degrees. We're told that the force is 800 newtons. We're told that the position vector is 0.7 meters. And so we can just use the definition of torque. It's just going to be R times F times the sine of the angle between those two directions. So that's going to be 0.7 meters times 800 newtons times the sine of 37 degrees. And that's going to give me 336 meter newtons. Well, that was just plug and chug. But now we've got a problem, because there's two answers that have that magnitude of 336 newtons. One out of the page and one into the page. Well, how do we determine the direction of this torque? Well, the direction is given by the right-hand rule for torque. Remember, you've got two right-hand rules. You've got one for omega and one for torque. The one for torque, you start at the pivot point. Okay, that's going to be the pivot right there. And you reach with your right hand from the pivot out to where the force is applied. Okay, so physically reach out to where that force is applied. And this is the important part. You turn your wrist so that you can wave in the direction of the force. That's going to force your right thumb in the direction of the torque, which in this case is out of the page. Okay, so the answer is D, 336 newtons. Does anyone see a problem here? That should be meter newtons. None of these answers are right. Everyone should have gotten extra points for this because it's got a flaw in it. My bad. Okay, but if those units were right, then the answer would be D. Okay. Now, we have a block of platinum that weighs 2.15 newtons. Now, you figured out that if it weighs this many newtons, you divide by 10. That means the mass of the platinum is going to be 0.215 kilograms. I just divided by 10. And I can also write that as 215 grams because there's 1,000 grams in a kilogram. Okay. Now I did that because the first thing I need to do to solve the problem is find the density of platinum. And that's going to be the mass of platinum, 215 grams, divided by the volume of this block of platinum, 10 centimeters cubed, and that's going to give me 21.5 grams for every centimeter cubed. Well, now we want to find what volume of platinum is needed to make a crown that's 1.72 kilograms. Well, I can write that the volume of the crown is equal to the mass, which is 1,720 grams, divided by the density of 21.5 grams per centimeter cubed, and that's going to give me 80 centimeters cubed. So the answer here would be E. Okay. So, Steve Iger run towards each other in a fit of rage. Steve Iger and Greg Francis. Steve has a mass of 80 kilograms, running at 6 meters per second due east. Greg has a mass of 120 kilograms, running due west with a speed of 4 meters per second. Just before the collision, each jumps towards the other, hurling insults. They collide and fall straight down to the ground with a powerful thud. Well, this is obviously a collision, so momentum is conserved. Now, before the collision, Steve had a momentum of 80 kilograms times 6 meters per second east. That's 480 franci east. Greg has a momentum of 120 kilograms times 4 meters per second, or 480 franci west. If I add 480 franci east to 480 franci west, I get 0. And that's exactly what they have when they collide and go nowhere. Now, the kinetic energy initial is not 0. Okay? Kinetic energy is a scalar. It's not a vector. So Steve's got kinetic energy. Greg's got kinetic energy. No matter what's going east, they just got energy. But at the end, their kinetic energy final is 0. And so that means that kinetic energy, which is the mechanical energy in this problem, is not conserved. So momentum is conserved, but mechanical energy is not. The answer would be B. Okay. Eldar builds a ring-shaped space station that generates artificial gravity by rotating How much torque is needed to make the 500-meter radius space station rotate clockwise at a constant speed? That's the important part. Constant speed of 10 radians per second. Well, if omega is constant, then alpha is 0, and we know that torque is proportional to alpha, with that proportionality being the moment of inertia. And so if this is 0, then this must be 0. So the answer in this case is C, 0. Okay, so now let's move on to the last page here. The velocity of a car on a straight road has been plotted as a function of time. Which following statements is true of the car? And is it speeding up? Is it slowing down? Does it have positive acceleration, negative acceleration? You remember that on a velocity versus time graph, this line here represents stopped. And the further we get away from stopped, the faster we're going. So as I go forward in time, I'm getting further away from the stopped line, so I'm clearly speeding up. So it's got to be A or B. Now, this is going to be velocity positive up here, and this would be velocity negative down here. So all of these data points down here have negative velocity. And if it's speeding up, we know that A and V are in same direction. And same direction means the same sign. So that's going to be negative acceleration. Now, another way you can see that is that the slope of the velocity graph is what gives you the acceleration. Okay? And here I have a line that has a negative slope. So I'm speeding up with negative velocity and negative acceleration. They're in the same direction. So the answer to number 11 is B. Okay. Here I have a 4 kilogram block accelerated from 5 meters per second to 30 meters per second in 2 seconds. This is a kind of a trick question. Okay. We know that P initial plus the impulse is equal to P final. And we're going to choose to the right to be the positive x-axis. That's the direction we're going to assume everything's going. Here I start out with 4 kilograms moving at 5 meters per second. And I put in the impulse, and I get 4 kilograms moving at 30 meters per second. Now, what about the 2 seconds, Greg? Well, that's the tricky part. That's the part that I should probably repent of, is that if I wanted to know the force acting on this block, I would need those 2 seconds. But the impulse is the combination of force and time, and so it's all bundled in there. So if I solve for the impulse, I get 4 kilograms times 30 minus 5, or 25 meters per second, equals 100 franci. So the answer is C. Now, in this problem, we have a velocity vector of 20 meters per second in this direction, and an acceleration vector that is making an angle of 37 degrees with respect to that velocity. And we want to know what the speed of the object 1 second later will be. So if this is what it is at noon, what would it be at noon plus 1 second? We're told that this acceleration vector is always going to be 37 degrees relative to the velocity. Now, that 37 degrees tells me that part of the acceleration is causing this thing to, part of this acceleration, that's got to be perpendicular, is causing this thing to turn, and part of it is causing it to speed up. So this would be A parallel, and this would be A perp. Now, if I use my trig functions, A parallel is going to be the 5 meters per second squared times the cosine of 37 degrees, and that's going to be 4 meters per second squared. So this object, whatever it is going to speed up by 4 meters per second every second. So if I look 1 second later, it's going 4 meters per second faster than it was. So the answer would be 24 meters per second. Okay, so the answer is again C. When a deep sea explorer is first tested in the lab, it is submerged in a liquid with a density of 1.5 grams per centimeter cubed and experiences a pressure 20 times the atmospheric pressure when it is 127 meters deep. If this is the maximum pressure the vehicle can withstand, how deep can it go in water? Well, we found that pressure increases by 1 atmosphere for every 10 meters of depth in water. Okay, so to increase, we want to increase from 1 atmosphere at the surface to 20 atmospheres down below. So we want to increase by 19 atmospheres. We need 190 meters of water. So the answer is E. Now, the last problem is the easiest on the exam. We have these beakers all filled, strange-looking containers with water. Oh, they're all liquid Z. I guess they're not water. But the important thing is that they're all the same liquid, so it doesn't matter what they are. We know that the pressure at some point 2 is equal to the pressure at the surface, which would be 1 atmosphere at sea level, plus rho GH. And we know that this formula is independent of the surface area. And so that means all of these are going to have the same pressure at the same depth beneath the surface. So the last answer is D. I'm going to turn off this recording before my software crashes again.